Hello, everybody. Welcome to episode 25 of the Hyperthesis podcast. My name's Liam.
My name is Pheely.
I'm Patrick.
And I'm Josh or something like that.
So today we're joined by a special guest, Josh Hainge. How do I say this? So me and Josh work together. He works for the same supervisor I do. He completed his undergraduate at Western University in Ontario. He did his master's in theoretical particles physics / UFT, I guess, at McMaster, and now he's studying transitions from integrable systems, the ones which have a chaotic classical limit. And he's also recently been studying some other things. But one thing I forgot to mention, Josh. So what we do is we start with an intro topic, which you can talk about it. You can chime in when you want. Then we have the main topic where we'll get you to talk about your stuff, and then at the end we tell a story. So welcome. Thanks for coming. I'm excited to hear what you have to say. But first, we're going to start with our intro topic. And today, I have an intro topic. I don't know if anyone else does, but normally I prepare something, but today there's actually some news for once. The closest known black hole to Earth has been discovered. So a stellar mass black hole called Gaia BH1, which I'm assuming stands for Black Hole 1 for some reason, was discovered to be the new record holder for the closest black hole to Earth. So it's this black hole about 10 times more massive than our sun, and it's located like pretty much in our cosmic backyard, as the article I was reading said. So it's 1,600 light years from us. As far as cosmic scales are concerned, is pretty close. It's a dormant black hole, so I think that means essentially that it's not sucking in anything, so no matter. A lot of black holes, they have kind of stars or mass falling into them, and it emits radiation, so you can kind of see black holes through these like jets of radiation.
It's weird as you say dormant black hole. Is it just mean the black hole just form around nothing? Well, there's nothing around it, so it's dormant? Because the event horizon is not like it's turned off, right?
Yeah, I think that's what astrophysicists mean when they say a dormant black hole, is that it's just that it's kind of in space in the darkness. It's not really doing anything besides existing and, having a gravitational influence on
Well, I know the big ones in the center of galaxies, they tend to refer to as active galactic nuclei. So I suppose rather than calling it a deactivated black hole, they go with dormant instead.
Yeah, deactivated black hole. I guess that's just a collapsed black hole if you want to. So how did they discover this black hole? The discovery began at the European Space Agency. The European Space Agency's Gaia Space Observatory, which I unfortunately don't really know much about, but apparently its mission right now is to catalog stars in our Milky Way galaxy. And while researchers were doing this, they spotted a star which showed this weird kind of distinctive wobble to it as it went along its orbit. And one way to find black holes, since they're hard to see because they're invisible essentially, is you have to see them through their influence on things. So like a black hole at the center of a galaxy emits a ton of light. Sometimes if there's a dormant black hole, you're not going to see it very easily, especially if it's really close to us. However, you can detect its influence. You can detect its existence through its gravitational influence on things. So there was this star going around its orbit, and they noticed that it's doing something it shouldn't be, unless there was this kind of invisible mass somewhere influencing it. So I'm assuming they noticed this data. They did some math. I don't know, probably some classical gravity Newtonian stuff, and then determined, all right, somewhere around here, there's got to be some mass about 10 times the size of our sun.
Well, that sounds similar to how they discovered Neptune, right? They sort of had seen all the other planets, but they detected an anomaly in the orbit of Uranus, and so they pointed to the sky and they said there should be something massive over here.
It's also interesting because that's why we think there's another planet in like the far reaches of the solar system, is because we're seeing very little perturbations within the orbits of Uranus and Neptune, and also some asteroids out in the Kuiper belt. So It's a very, I guess, universal method for detecting astronomical objects.
I feel like most modern discoveries or instruments don't directly measure or observe things anymore, right? You observe the effects of things. Like all particle physics are just like, observing what would the residue, what would happen, guess the process. It's not like to throwing a projectile, you can see where it lands. You think about any labs I went to on the tour. I was like, especially photonics or quantum stuff, like nobody observed anything directly anymore, which is pretty interesting. That maybe it's an existential question. If you only see the effects of it, never see you only hear the quack, but never see the duck. But you assume there was a duck. That's to me that's like quarks. They're like, oh, I see all these stuff, but you see the electromagnetic field that happened from it that supposedly occur, or some energy that got released. Like, have anyone seen electrons? Maybe there's only one electron.
Stop bringing up the one electron theory. How dare you? That's so funny though. We mentioned that before. We have to do an episode on it at one point, just because it's so wild, but really silly at this. I don't know enough about particle physics to say anything about quarks and that kind of stuff. But there's this. I've been getting into like symmetry and QFT a bit recently, and I think Josh knows a lot more about that than I do. But there's this whole wonderful mathematical theory that describes them, and they're real, they're a thing. But yeah, I guess I've never seen a quark, so.
Yeah, it kind of depends what you mean by see, right? People use that word pretty colloquially, and they don't always mean directly see it with your eyeballs. So, Liam, I don't know if you remember when we went to Waterloo to that optics institute for that Toucan conference. Some of the lab tours, they had pixels on the screen which were showing you where the atoms were sitting in their trap. So I don't know if you would count that as seeing something. Or for example, back in the old school days of particle physics, when people were using bubble chambers, you could see the streaks of the charged particles moving through these bubble chambers. So you're not seeing the particle, but you're seeing the effects. And somehow the whole point of physics is to equate those two things, right? Like if you see the effects you expect from something you've described, then you've seen the thing itself in some sense.
Yeah, I feel like the effects is the thing, right? Because you think about all particles, if you think of it as wave, right? You don't see them, you just see the photons that got absorbed and re-emit, or just emitted from it. Right? So what we see are not the actual things, because it cannot be seen. The photons can be seen.
I mean, get into this whole like the particle a wave. I mean, yeah, but then you look at it and then it becomes a point particle somewhere, and like point particles confuse me. I don't think point particles make any sense, but they work really well with the math. And anyway, it's this whole huge rabbit hole we could go down forever. But
well, what are you measuring, right? If you're trying to make a measurement in the position eigenbasis, you're going to pick one of those positions out, and then it looks like a point.
Yeah, that's anyway. We don't want to scare people with. I mean, we don't have a set skill level that we talk about here. We kind of jump between like trying to keep it as simple as possible, and then we'll randomly talk about like eigenvalues,
right? Okay,
and, like stuff like that. So don't feel afraid to talk about it, but yeah, maybe not. Maybe we should move on to the main topic, just because I wanted to keep the intro topic fairly short so that we can hear what you have to say.
Sure. Oh, actually, I should say at this point, I think you might have said at the beginning I did my master's at McMaster, and
or was it Waterloo?
It was Edinburgh.
Oh, okay. Yeah, sorry. So, all right, you have to tell me. You have to tell us about that, because you came to McMaster and you worked for Cliff Burgess on QFT, and now you're working for Duncan. So I just kind of assumed you did your master's with him.
No, yeah, I couldn't hack it with Cliff, honestly. it wasn't a good fit. I wasn't a strong enough student, I think.
Fair enough. But anyway, so tell us. So I'm not sure how I should start this, but what do you do now? If you can, somewhat short, I say shortly, longer than what I summarized at the beginning. But what are you researching now?
Sure. I guess right now there's two sort of things that I'm looking at. I've been distracted lately by this other interesting project that we could get into if you want. But the project that you mentioned in the introduction is sort of this transition from integrable systems, which I guess if you want to lower the level a bit, is somehow like a predictable system, right? You have things about your system, conserved quantities, you might say, and that makes the equations of motion easy to deal with, and so you can sort of predict what's going on. But a lot of those systems, if you perturb them a little bit, then they become chaotic. If you're thinking of a classical system, that means, I don't know. I'm trying to keep the level appropriate now. You got in my head, but the trajectories in phase space would diverge exponentially, right? Which basically just means if you think of the double pendulum, after a little bit, these two things could start at a very similar initial point, but they'll end up swinging around in wildly different directions. So I'm looking at basically a quantum mechanical version of that.
Nice. So we did an episode last week on chaos, so I'm hoping whoever listened to that can be up to date on what it means roughly.
Yeah, what I'm actually a little confused about, because last week we talked about chaos and that it works only on the deterministic system by construction. We just defined as a deterministic chaos. Well, that quantum mechanics is stochastic. So how does that work? Is there something like stochastic chaos?
There's something like stochastic chaos. Well, I think maybe I'm not knowing exactly what you mean by stochastic. When I hear that word, I kind of think that you're putting in some sort of noise into your system. And so you're drawing some values from probably a classical probability distribution, and you're using that to sort of jiggle your system around a little bit. Is that what you mean?
Well, what I meant by stochastic is quantum mechanics is a theory of probabilities. It's not deterministic in a sense that as the same as classical mechanics. The probability is the distribution around instead of just like the standard equation of motion. And I don't know if chaos is well defined in that quantum mechanics.
Yeah, like I always hear people say there's this branch of physics called quantum chaos. I always hear people say, technically quantum chaos isn't a thing because quantum mechanics evolves unitarily. There's this unitary operator that tells you how an initial state evolves as time goes on, and it's because of that you can't really have chaos in quantum mechanics. How does that work? I think it's something to do with like a quantum chaos is a system is kind of trying to like describe how you can have a classically chaotic system, yet you have something that's not chaotic quantum mechanically. I'm not sure.
Yeah, so I guess I would say I don't think it's necessarily the unitarity that prevents it from being chaotic quantum mechanically, because you can describe time evolution in classical systems with unitary operators as well, and you can still end up with a chaotic system. For example, I think you can write down the Baker's map using unitary operators, which is this sort of paradigm of classical chaos where if you imagine like stretching some dough and you fold it in half and you stretch it again and you do this kind of thing. Except I think it moves around a square in this picture, but it's sort of the same kind of idea. Really, I think what prevents a quantum system from being chaotic in the sense that we mean it classically is that, well, first of all, your phase space is discretized in quantum mechanics, right? You've got these sort of regions in your phase space which are of size h bar or h. And so you sort of lose the ability to talk about trajectories in quantum mechanics because you can't pick out points in phase space. You can pick out small little volumes in phase space. And once you start picking out little volumes, if you want to make contact with the classical theory again, then you start to talk about ensembles of trajectories, right? And normally, so I'm not super up to date on my classical chaos theory, but the way that I think about it, when you have a chaotic system, one of the ways that you can notice that is you can pick 2 points in your classical phase space that are very close to each other, and you can time evolve them. You can see that on, I think, short times, they diverge exponentially in phase space, right? But with an ensemble of trajectories, it's kind of, you can't really do that. The other way to see it with quantum mechanics is that it's quantum, right? So your energy levels are discretized, whereas in classical mechanics, in principle, every available energy level is there. You've got a continuum of energy states. And so if you think about a unitary operator now, if you have a finite number of discrete energy eigenstates, after some amount of time, the system will come back to itself, right? Because you have only a finite number of periods of oscillation of things in your system. And so every once in a while, they're all going to line up again and you come back to where you are. In classical mechanics, that's not true, right? Because you've got the continuum of energy states. And so you're not I mean, there's this Poincare recurrence theorem, which says you can come back arbitrarily close to where you started, but somehow that's distinct from the quantum mechanics situation in a way that I don't fully understand, if I'm being honest. But the argument is usually given, I think, in terms of these discrete energy levels.
Are you saying because quantum mechanics is that the discrete nature of it makes it become like the chaos doesn't manifest?
Yeah, or you have to somehow think of chaos in a different way, right? People have different measures of what they call chaos in a quantum system, and that can have to do with these out-of-time ordered correlators, which I haven't dealt with a lot, but which one of our former group members dealt with. There's also these Low-Schmidt echoes. I guess that's more like a dynamical phase transition thing, but maybe it's an open question whether or not the transition to chaos is a dynamical phase transition. I'm not sure.
Can you use something like the Lyapunov exponent in quantum mechanics? Because like I don't know how to do that. Like with like probability distribution.
Well, I know there is a way to tie a Lyapunov exponent to this out-of-time ordered correlator that I mentioned, but like the student that graduated recently from our group, Wyatt, he studied these OTOCs, right, out-of-time ordered correlator, and he showed that you could actually end up with an OTOC that would look like a Lyapunov exponent, which is telling you should have a chaotic system, but the system is completely deterministic. And so I think it's one of those things where it works a lot of the time, where you can relate this OTOC to a Lyapunov exponent and talk about chaos in a quantum mechanical system. But you have to be a little bit careful because it's possible to somehow break that correspondence.
Everybody here actually knows Wyatt.
Oh, okay.
It's kind of nice because we all went to the same university.
Oh, right. I always forget that.
Yeah, I forget that too sometimes, but I want to get him on the show eventually. Or maybe I should. Maybe we should get back. So you're studying this kind of stuff, but how are you doing it? I know in our group, we usually study Bose-Einstein condensates in some way. So how does that tie in, and what are you doing?
I guess the starting point, like Liam said, is a Bose-Einstein condensate, and the system, I guess I always have in the very, very back of my mind, because I've abstracted so far away from it, is a Bose-Einstein condensate in a double well potential, right? So if you think of like a W shape, you've got two sort of minima in that potential, and your Bose-Einstein condensate can sit on one of those two sites, and the particles in the condensate can sort of, I guess, funnel between the two sites. And it turns out that this system can be mapped onto a Bloch sphere for, okay, let me take a step back. So if I have an n particle Bose-Einstein condensate, and I've got these two well sites, then I can do a formal mathematical mapping, which will take this system into the system for a fermion that has spin n/2. I guess it doesn't have to be a fermion. And these spin systems you can map onto a sphere, which gives you like a nice geometrical representation of what's going on. And you can sort of say that your z coordinate on the sphere is telling you how many particles is in each well, right? So I could say if my vector on the sphere that's telling me which state I'm in is pointing all the way up at the North Pole, then that would correspond to all of my particles being in, let's say, the left side of the double well. And as I sort of turn this vector down in z, so I'm getting closer to the equator, that would mean that the number of particles in each of my wells is starting to balance out. And then as I go down to the South Pole, that would correspond to all my particles going into the right well.
Or is it something like a order parameter if you do stat mech, or you can like, oh, well, I'm going to define something that basically tells you order. So if it's one, it's all the states in one well. It is -1 is in the other. Is it something similar to that, like magnetization?
I suppose you could, because essentially what I'm doing is I'm mapping the operators from the original system onto angular momentum operators. So if you wanted to think about your SZ operator as like giving you some sort of order parameter, I suppose you could do that. That's not the way that I'm used to thinking about things, but it doesn't seem unreasonable to me. But yeah, so once you put the things on this sphere, I do my first approximation. Well, there's a little bit of approximation getting to the sphere picture. But if you sort of now focus your attention onto the equator of the sphere, so what you're basically saying is that the number of particles in each well, they're pretty close to each other. Then the math of your Hamiltonian simplifies a bit. And it actually ends up looking exactly the same as the Hamiltonian you would have for the nonlinear pendulum, right? So if you just think of, if I have a string with a weight on it, right, it'll look like that Hamiltonian. So there's a kinetic piece for this string moving with some angular momentum. And then there's a gravitational potential piece, which goes like the cosine of the angle from the vertical. So you can end up with something very similar to this Hamiltonian. And to make contact with the chaos, what we're doing now is we're pretending that in this double well potential, which we have in the back of our minds, we can turn the barrier between the two wells on and off. And we can do that in a periodic way. And we can do that using a delta function to make things easy, right? So we can pretend that the barrier is basically off all the time, but then we turn it on every so often periodically, and it just shoots up. And this now in our sort of pendulum picture would correspond to something called the kicked pendulum, or the kicked rotor, or the kicked rotator. And again, it's the same sort of picture, but what you're pulsing off here is the gravity term. So the cosine potential term is always off except for an instant when it's on. And this is a very, very well-studied system. It's, I think, the simplest, or one of the simplest systems in which you can have chaos, because it's a one-dimensional system. But because you've got a time periodic Hamiltonian now, you're able to introduce some chaotic dynamics.
Okay, so to like summarize that, you have double well potential, Bose-Einstein condensate. And for maybe people who don't know, essentially there's two main kinds of particles. You have fermions and bosons. Fermions are things like electrons where they can't occupy the same state. So one kind of, I guess, naive way to think about it is you can't shove two electrons like together. I guess that's not quite how it works, but they can't be in the same state. They have to be slightly different. And then the other type of particles is bosons, and they can be in the same state. So you can get this thing called a Bose-Einstein condensate, where if you basically, the typical example is you take a gas, some gas of bosons, and you make it really, really cold. They all kind of macroscopically occupy the lowest energy states. They all kind of pile up on top of each other. One way to think about it. You're studying kind of Bose-Einstein condensate, and one thing you can do with ultra cold systems really well is you can do pretty much a lot of things to them. They're really easy to manipulate and study. I say easy, that's a relative term, but in theory they're easy. So a lot of the time what you do is you take these ultra cold systems and you study them, and then kind of maybe apply them to what you learn from them. You can apply to other systems later, which is like a good reason why you study them. So you're studying this double well, and you can map it to, so you can mathematically say it's equivalent to a kicked rotor, which is kind of a simple example of classical chaos, even though you have kind of a quantum system.
Yeah. So I suppose really what I should be saying is that I now have a quantum mechanical system whose classical limit would correspond to a chaotic system, right? If you want to be a little bit more careful about your words and not say quantum chaos, right? I think Michael Berry advocates for the term quantum chaology instead.
I read on Wiki he's somehow responsible for quantum chaos in some way, although I don't really know.
It's all his fault.
Seems to have done everything. I don't know.
He's got his fingers in a lot of pies, I think. But yeah, he's definitely done some work on these systems. I think it tends to come in, well, maybe I shouldn't say too much because I've been distracted by this other project, so I'm starting to forget the literature on the quantum chaos stuff a little bit.
Oh, before we move on to your next project, I want to ask more of a lighter questions. So what we ask all our guests this, what got you into physics? What are your hopes and dreams?
What are or what were? Because those are no longer the same. Yeah, I don't know. I wasn't a super athletic or popular child, and I liked reading and doing puzzles. So I kind of did that all through my schooling. And then when it came to high school, I know that I was kind of bored in most of my classes. So I would goof off and my marks would still be pretty good. But I remember in grade 12 trying to study for this one physics test because there was something I wasn't understanding. I think it was just projectile motion, these sorts of questions where you've got an airplane and it drops a package and where does it land? And I remember I studied for the test and I didn't do any better than I normally did. So I got kind of mad. And I tried to study for the physics class from that point on. And my marks went up a little bit, but they weren't phenomenal. It wasn't my best class. Not that it was bad, or even my worst. But so I kind of I got a little upset, and I was like, well, I'll just take physics in university, and I'll come back and I'll destroy all this stuff. Um, so originally in university, I took physics and material science with more of a focus on material science, but that's sort of shifted over the years, obviously.
I never heard anyone got into physics out of spite before.
Yeah.
That's really funny, actually. Like I got into physics because I like knowing things. I guess I always hear these people say like, "Oh, it's the not knowing that's the most fun," and I'm like, "Yeah, that's true, but it's also really upsetting and angering." Like when I look at something, I'm like, "Why is this happening?" And it just like upsets me that I can't figure it out.
But I mean, that's the same thing, right? There also was this curiosity there, and I liked the subject material. And you know that eventually you get to learn about cool stuff like particle physics or gravity or whatever else. But
So during your undergraduate at Western, you did research, I think, right?
yeah,
Can you tell us what you did there a little bit? Well, actually, maybe you should tell us about your hopes and dreams, Pheely, first. Always interested in that.
yeah, okay. Well, I'll answer the sort of the two at the same time. What were my hopes when I was in undergrad, right? So I honestly I was just trying to have a good time. I thought physics was interesting, so I tried to stick with that. But I did have this idea in my head that I wanted to I don't do something like important, right? And at the time, plastics seemed like a big issue, so I figured I'll go into material science and I'll come up with some biodegradable plastic that everybody's going to use because it's so much better than the stuff we have now. But then I wasn't very business minded, right? So they have these things, they had those things. It's just that people aren't using them, although it's getting better now. So because of this material science component to my degree, I took some chemistry courses and some earth science courses. And one of the earth science courses that I took was mineralogy and crystallography. And I remember in second year, I was trying to be a little more gregarious. So I was kind of doing the yes man thing of just if anybody asked me to do something, I would do it. And in class one day, the professor asked if there were any volunteers for the London Gem and Mineral Show, which is just an exhibit in London every year. People bring some stuff to sell, and Western sets up a little booth from the Earth Science Department. We teach people about minerals. So I signed up for that. It was a good time. I showed up to the event. It was maybe, I signed up for a 4 hour shift. And after about an hour, there was sort of a lull at our booth. So the professor said that I could go and walk around and take a look at some of the stuff, come back, finish out my shift. And I said, okay, cool. So I went and I looked around, and there was just so much cool stuff there that I got distracted by. I ended up coming back about 3 hours later. My shift was over. I thought she was going to be furious. I was so apologetic, and she was just happy that I was enjoying myself. So that was it for that. And at the end of the year, during my final exam for the course, without having had much other interaction with her other than asking questions in class or whatever, she came up to me during my final exam and she started to have a conversation with me, right? So she asked me, how's the test going? I told her, oh, I'm basically done, but I'm sort of stuck on this early multiple choice between these two answers. I'm trying to think it out. Everything else, I think I have. She says, oh, okay, cool. Have you ever thought about doing research in the summertime? I was like, no, that sounds like it could be interesting. So she introduced me to the concept of the NSERC USRA. So we had a little bit of a chat, decided I would apply for that after the exam. And as she was leaving to go proctor the rest of the exam, she sort of pointed me to the right answer on the test, which I thought was kind of funny. So I did research with her for the summer in an X-ray diffraction lab, and that was really cool. I got to shoot lasers at meteorites, basically, and figure out their chemical composition, or mineral composition, I should say. That was how I got into it. And then that sort of really sparked, oh, I like research. I think I can do this for a living. So my dream was to continue on in research. And now I'm not quite sure I'm cut out for it. I kind of like the teaching aspect. I think I'm better at that than the actual research component.
Yeah, I think as graduate students, we have this challenge that come up often, like what do you want to do for your life, right? Some people say they want to do industry, they want to go to R&D, research and development stuff, and like some people love to teach, or some people wanted to do a lot of research and then they fell in love with teaching. There's a lot of things that, is a factor into our decisions, which I think we are pretty, we still have some time to think, right? So hope that we all got this figured out.
I think a nice thing about a physics degree, I mean, I'm always told that you can do a lot with a physics degree. I don't know how true that is, but I do see a lot of, like, I know physicists who became lawyers, or they work for banks, or work for tech companies, and so on, so on. one. So I think people just like the fact you can do math, which is nice. And yeah, I know people who've gone on to be teachers, and like I don't know. I like research and I like teaching. So right now, kind of like a physicist, good combination of that. But yeah, I definitely have my doubts sometimes.
Yeah, I think I don't know, my passion still sort of lies with the research. I don't think I could ever give that up fully. It's just that I'm not convinced I could make a living off of it. So my interest has shifted a little bit more towards the teaching side, because I find you learn when you teach, right? People say that all the time, but sometimes you get asked a question that seems silly maybe, and you have to think about the answer. And or sometimes a student will ask you a question that makes you think about a topic from a different perspective. And I think it makes you stronger to teach.
I always thought it was interesting that I know some teachers go when they get their master's or their PhD, and then they go and teach like high school or something like that. I always find it interesting that they don't try and like how I know how do I word this? Why don't they do research in their spare time? They enjoy it. I mean, maybe they just don't enjoy it and they don't want to. I guess it's harder to publish if you're not at a university. A lot of journals won't accept that. Maybe I'm not sure.
I think it's mentally taxing, and these days, especially like new theory require not just pen and paper. Now you need like resources. You need maybe computational resources if you want to do theory, and it's hard. Like in university environment, like I think there's a lot of like advanced ideas being talked about rather than in high school and stuff, right? Because according to my friend who taught high school, he's like, yeah, it's like 90% babysitting, and you kind of have to deal with kind of these simple concept. Even now when we go to the the undergrad, so we look back at those theories sometimes from undergrad, it's like, well, those are really simple concepts that we were struggling to learn at the time. But looking back in retrospect, those are like, all we did in undergrad mostly just linear systems, which is like chill.
If I may steer the conversation back to Josh, so you did some X-ray work for your undergrad. So I guess moving forwards in your academic career, for your master's and now for your PhD, how did you kind of decide on those different topics?
So I guess I mean, I'm not entirely finished with the undergrad, I guess, to answer that question. So I did an internship, and I ended up working at a company doing R&D, industrial R&D, at Lanxess when they were still in London. And I was looking at developing a tire inner liner compound. So I was still sort of on the material science trajectory a little bit. I liked working with the rubber. I made this new inner liner. It was really impermeable. I thought I did a great job. And I really liked the research that was going on there. So I thought that I would just try to get a job there after I graduated. But the year after my internship, they actually shut down and they moved to Singapore. So after I graduated, I was kind of like, well, crap, what do I do now? But because I had done that internship, I was now like a year behind, in quotes, everybody else that I went to school with. And so my girlfriend at the time ended up graduating university before me, and she was applying to vet school. So she applied to Guelph, she applied to, I think, Washington, and she applied to Scotland, the University of Edinburgh. And the Guelph application process got messed up somehow. They tanked one of her references, so she didn't get in there. And she ended up getting into Scotland. So she went there, and I thought, I would go out there. That sounded pretty fun. So when I finished school, I applied for a 2-year working holiday visa, they used to call it. Now it's like a tier 5 youth mobility scheme thing. Commonwealth countries all have this nice agreement where if you're under 31, and you've got like $5,000 in your bank account, they'll just give you a visa to go work in some Commonwealth country for 1 or 2 years. So I went to Scotland. I worked for 2 years, tried to get some sort of research job there, but my money started running out. So I took a job working the night shift, stocking shelves at a grocery store, and I was so bored that I started listening to YouTube videos of Leonard Susskind on particle physics. And I downloaded this textbook, I think it was David Griffith's maybe textbook on particle physics. So I started sort of reading at lunchtime, listening while I was stocking the shelves, and I got really interested in particle physics. And when my 2 years was up, my girlfriend still had a year left in vet school. So I just threw a Hail Mary at the University of Edinburgh, and I applied for their master's program and somehow got in. And So that was super fun. It was a course-based master's. I took a lot of courses on QFT, like Liam said. And then my thesis was like a 3-month summer research project where I was looking at some data from the LHCb detector, and that was really fun. But then afterwards, my girlfriend and I graduated at the same time, and we decided to come back to Canada. So I was applying to some universities for a PhD position, and Cliff Burgess at McMaster was the guy who sort of said yes. So I started here with him, and I really liked the projects, but there was some turbulence in my life and it wasn't going well. So I took some time off school. Then I came back with Cliff, slightly different project, still interesting, but I just didn't have the aptitude for it. And so he sort of suggested that maybe I would be a better fit in Duncan's group. So I switched over to Duncan, and I think that was a really good decision. I really like the research. But that's how I sort of bounced from like a particle physics to Cliff, where I started particle physics again. And then when I came back on the new project, it was more gravity focused. And then now with Duncan.
Yeah, Cliff is so Duncan's a really great supervisor. He's very chill, he's understanding. He makes a lot of time for you. Cliff is the same way. I actually really like Cliff, but again, I've never had him as a supervisor. He's just on my committee. But like he's a serious physicist. He's at Perimeter Institute. His supervisor was Weinberg, a Nobel Prize winner. I'm in this QED class with him right now, and he comes in with this massive like binder, and he just like whips it on the table. And he's like, "All right, so these are my notes from Weinberg's QFT class. We're just gonna go through them." And I was like, "Oh my god!" But I think, yeah, his style of work is a lot more intense, especially if you have some turbulence in your life. And I find, like, especially with COVID happening, working for Duncan has been very good. I can kind of work on my own terms, which is how I function. I think if you work for Cliff, you have to be one of those like 9 to 5 style people, whereas I'm not.
So we know you're working with Duncan now, and we've heard a bit about some of your research, but tell us some more. What else are you working on?
Well, okay, so I guess lately I've been distracted by another project. So Duncan took on some students in the summer to do some research, and he kind of picked out his graduate students to help pseudo co-supervise one of them each. And so the student that I was kind of helping him watch over, I think because I showed interest in the project because it seemed like a neat question, is having to do with the so-called Abraham-Minkowski controversy over what the momentum of light in the medium is. And well, I guess just to sort of undercut the fact that I just used the word controversy, it has been resolved. It turns out that it's sort of an arbitrary choice. And we can circle back to that. But back in ye old days, when people were wondering what is the momentum of light in a medium, there's sort of 2 sets of simple arguments that would lead you to believe that the momentum of light in the medium is either increased by the refractive index of the medium, so the momentum of light would go from p to p times n, say, or it's decreased by the refractive index, so it goes from p to p divided by n. And the first one I said, the p times n, that was the form proposed by Minkowski, and the momentum decreasing in the medium, that was proposed by this guy named Abraham. And it's weird, right? Because it should be obvious how the momentum of light changes in a medium. If light goes into the medium, it's moving in one direction, and then it goes into the medium, and somehow that medium should keep moving in the same direction that light was moving in, right? Because the light just hit it. And so that means that the momentum of the light inside the medium should have to decrease because the block is now moving. It's taken some of the momentum. It must have left the light. But if you think about Snell's law, right? Let's say light coming in to a surface, and it hits and it refracts and it bends towards the normal, right? Well, momentum conservation is broken in the direction normal to the surface, but in the direction parallel to the surface, it should be conserved because you still have translation invariance. And so the fact that it bends towards the normal means that my vector in the downward direction, my momentum downward somehow must have increased, right? So now it looks like momentum has increased. So which one is right? And it turns out that if you treat the light as a particle, then you'll end up with the Abraham result, which is that the momentum of light decreases. Whereas if you treat it like a wave, it looks like the momentum of light increases.
Yeah, weird thing about this stuff is that to me, light through mediums are process of absorption and re-emission. It doesn't just go through the atoms, right? It's like, so momentum in a way is like, it's that the total energy must be conserved, the total momentum must be conserved, but there's more that happening inside inside the medium than just light passing through, right? Like, I think it's just a little
I
complicated.
think that's a misconception that light passing through a medium is just absorbing and re-emitting. There's more to it than that, and there's like wave effects. And something I actually want to talk about at some point, but I don't know enough about it to talk about it now. But there's wave effects and coupling and all kinds of stuff happening, not just absorption and re-emission.
So, I mean, if you're interested in looking at that, I would say that the Fermilab YouTube channel actually put out a video on that a few months ago now, I think, which is really good. I like their channel.
Okay.
But yeah, because I mean, you want to think of maybe light being absorbed and re-emitted, but emission is sort of a spontaneous process, right? So it's going to get re-emitted in every direction. Well, then how do you end up with Snell's law? How do I know which way light travels through the medium? Because it comes out on the other side. I can measure it.
So how are you? I mean, I've attended some group meetings and I've seen some things you guys talked about, but how are you kind of approaching this problem? What are you doing if you say it's been resolved as the resolution is that it depends how you look at it, but still I don't know if I still like that.
That's exactly it, right? I think everybody knows the answer, but it kind of just doesn't sit right. So yeah, it basically boils down to, like Pheely said, the total energy has to be conserved, the total momentum has to be conserved. And so that means if you're going to do the physics for this system, you should be writing down some stress energy tensor for the energy and momentum coming from both the light and the medium. But then how you want to split up the components of that stress energy tensor, that's sort of what's artificially giving rise to this controversy that's no longer a controversy. But I guess we're sort of thinking about what does an atom do, right? Like, again, we somehow know the answer, but it just feels wrong. Because if I have an atom, a single atom, and I shoot some light at it, and the light is going to change the momentum of the atom somehow, I'm pretending that I can treat this atom as a dielectric medium, right? So it's got some refractive index, and that should be fine as long as the light isn't likely to be absorbed by the atom if it's off resonance, right? So the light passes through this atom. The momentum of the light has to change in the atom somehow. And that means that the momentum of the atom has to change somehow. But that means that I should be able to measure how the momentum of the atom changes, right? And if the momentum of the light decreases in the medium, then the atom must have gotten pushed forward to compensate for the loss. But if the momentum of light increases in the medium, then the atom should have to move in the opposite direction in order to compensate for the increase. So it seems like there should somehow be a concrete answer, even though we know that the split is arbitrary, right? Which way does the atom move? So that's kind of the question that we're considering right now.
Yeah, I think these theories, it came down to, I think, the like two ways to do physics or science, right? The way Snell and Newton came up with these things are more like phenomenological, where they just build theory from the top down, right? They see the effect and they're like, okay, these are the equations that describe it. Doesn't matter what's lying in the bottom. And now in the postmodern world that we are in, we are interested in like, oh, we're building this standard model or these quantum mechanics and stuff, and try to make it fit all the things that we observe. And to me, that's very difficult because, like now, like you said, you were talking about it, right? You try to make an idea of what the atoms is behaving and how the lights affect that atom, rather than you think about when Snell's like, I don't care about those stuff. I see the lights come in. I know how I see the ray of light, how it diffracts. It doesn't matter what lies under it. I think it's a really interesting question. It's hard. It's difficult because you try to come up with a model that works to describe this, but there are two conflicting models that somehow have logic. Like logically, they both make sense. I listen to it. It's like, yeah, it makes so much sense, but there's only one truth.
Yeah, well, I mean, the crazy thing is that there's experimental support for both, because depending on what you want to measure, right? If you're trying to measure the particle properties of light somehow, then you'll end up with the Abraham result. But if you're trying to measure wave properties of light somehow, you'll get the Minkowski result. If you throw up like a mirror that's on like a little torsion ribbon or something, and somehow because you've got this torsion ribbon, what you're doing is you're going to be coupling to angular momentum because this thing is going to twist. But the Minkowski, I think it's a Minkowski formulation of the stress energy tensor for light in the medium. It's not symmetric. It's not a symmetric tensor. And so it doesn't conserve angular momentum. And so I think, if I'm recalling correctly, if you try to do an experiment where you're somehow coupling to angular momentum, what you're going to do is end up with a result that somehow looks like it disproves the Minkowski form for the energy momentum tensor of the light in the medium. But there's always sneaky ways to fix it, right? It's like, oh, you forgot to add this term to the momentum in your medium, or you forgot to think about this in your setup. And so it can always be corrected back to, maybe I phrased that poorly, but you can always somehow weasel your way back into saying that, well, you actually didn't disprove this energy momentum tensor. And so it's not simply a matter of looking at what happens and then saying, well, this is the one true theory, because depending on what you're looking at, you get support for either formulation, right? Just like in a double slit experiment, if you want to look at the wave properties of the particle going through the slits, you have to just let it hit the screen and it piles up and you look at the interference pattern. But the screen itself is measuring where the particle hits, right? Where does, and I just use the word particle, right? You get a flash on the screen. So it was something localized there. So that's measuring the particle property. So the tricky part about physics now is that it matters what you're looking at. What are you trying to detect?
Yeah, and that's kind of the weird thing about quantum mechanics, I guess, is how you measure things and what you're looking for and all that good stuff.
Another question for Josh. All your work sounds like very theoretical now. Like, what was your experience? You did some laser material stuff. There's probably has some experimental part. Like, so what steer you into theory instead of experiments?
Yeah, that's a good question. And I'm not sure that I really know. So in my undergrad, I was doing X-ray diffraction experiments, working with meteorites. That was super cool. I thought I wanted to make plastics. And so I was very like materials focused. But I think it was a combination of just being more interested in the theoretical side of things, like the cool math that I got to do and all the cool concepts that I got to learn about. And it's not that I was a terrible experimentalist when I was in undergrad. I'm sure I am now. But I think I wasn't quite as good as that either. My lab marks were always a little bit lower than my marks in my other courses. So I ended up switching from, so at Western, you can do like an honors specialization in something and you can do a major in something. So I did an honors specialization in material science with a major in physics. So what that meant was basically my credits were like not 60% focused on the material science. And I was going to do my thesis on that. And then it was about 40% focused on like the pure physics that you learned in undergrad. But I ended up swapping that partway through. So I did 60% physics, 40% material science, although I still did do my thesis with this teacher who got me into X-ray diffraction. She was great. I worked with her for like 3 years. And then like working the night shift, I don't even remember. Somehow like the YouTube gods knew what to feed me in my algorithm at that time. And so I ended up learning particle physics from Leonard Susskind, which was great. And I think just because I happened to click on those videos, probably there was something big going on with the LHC, because I would have graduated around 2014. So the Higgs boson stuff would have been pretty big, pretty fresh. And probably I wanted to learn more about that. So maybe that's why it came up in my feed. And I just sort of stuck with it. I just kept getting more and more theoretical. And then the problem with Cliff, I think, was that it was just pure theory, like pencil and paper. And so when I got stuck, I was stuck. But at least with this research I'm doing with Duncan now, I can flip between, there's a little bit of theory. I've got 2 different projects going on. I've got some numerical simulations I can run. So there's some coding aspect if I'm stuck in the theory, and I can bounce around a little bit more. But it is a bit, even though it's still a theory-based project, it's a bit more towards the experimental side, simply because I'm able to use my computer to run some experiments, let's say.
Some butterfly effect in action that you just clicked on one YouTube video and here you are years later. If you had clicked on a different one, your initial condition was different. You've been, who knows, biologist right now.
Yeah. Well, I mean, if Lanxess hadn't shut down in London, I probably wouldn't have gone to the UK. And so the girl that I was dating at the time, I'm now married to, right? So if I had managed to get a job at Lanxess, my life would be completely different, right? If I'd managed to get a job when I went to Scotland instead of having to work the night shift, then I would be in a completely different place. So that's pretty common for most people.
Well, thank you very much, Josh. We should wrap up soon for the sake of time. I don't know if you had one last thing to say, Pheely.
Yeah, it was. It's really interesting to hear these different stories because I think former guests we had, sometimes we had people who are like knew they want to be physicists or scientists since high school, since they were really young and they follow very rigid plan, right? And Josh's story is very spontaneous, like just click on here, just curious, and just There are a lot of paths you can take to be scientists, and a lot of scientists, once you talk to more of them, they have like sometimes vivid stories about their lives that you don't see, because people think the scientists just stare at pen and paper, maybe do some lab work, but there's this like a myriad of differences between scientists and between like our backstory, which is pretty fun. Thank you,
Yeah,
Josh.
thanks so much. That was good. That was good to hear about.
Thank you.
I've heard about a lot of this stuff before, but it was good to hear other people's questions on it instead of just my own.
Yeah, it was fun. Time actually flew. I thought I was going to run out of things to say.
We're not quite done yet.
Good.
I'll give a short story Patrick will tell us. But before that, he's going to tell people how to contact us.
Right. So if you are listening to the show, obviously you have found us on some sort of podcasting service, or you're listening on YouTube. So we can be found at pretty much wherever you get your podcasts. So we're on Apple Podcasts, Google Podcasts, Amazon Music, Spotify. We're based out of Anchor FM, and we now have a YouTube channel. So you can search up Hyperthesis Podcast on YouTube, and you'll be able to find videos. They actually look very cool. Pheely did an excellent job with the render settings for them. And so go check out our YouTube videos and feel free to leave a comment. Also leave a review if you can on your podcasting service. If you would like to contact us directly, you can send us an email. We're hyperthesispodcast@gmail.com. We also have an Instagram, so you can follow us on Instagram for updates with the channel. We post every time we post an episode. And we also post some behind the scenes content. So we're at the Hyperthesis, where you can enjoy all of our content. And of course, we have links to each episode. So make sure to subscribe, like, heart, follow, however you do your thing on whatever social media. Just feel free to send us questions, or if you're interested in being on the show, much like our special guest today, also send us an email. And Josh, is there a way that people can contact you if they have questions about your research or life story?
Ooh, not really. I'm not a big social media guy, but you could always Google the list of McMaster Physics graduate students and find my name on there. Feel free to send me an email. I'm more than happy to talk about my research.
Perfect, yeah. Or you can send us an email and we'll make sure it gets forwarded to Josh, and we'll try and work out getting you an answer. So yeah, feel free to reach out to us on any of the platforms that I've mentioned before. So going into the story, it's, I guess, not so much related about today's topic, but kind of culminates past two episodes in a roundabout way. So we have talked about a lot of chaos, whether it's chaotic systems like the Big Bang and the universe itself, or some quantum chaos, or whatever term you guys said earlier that we're supposed to be calling it now, quantum chaology. Yes. So we've been talking about chaos a lot, and as we've been discussing today, we're trying to figure it out. We're trying to make, I guess, simplifications, or we're trying to figure out ways in which we can better understand chaos and chaotic systems and what happens when chaos is thrown into a system. So physicists and chemists and other scientists have been trying to better understand these chaotic systems for centuries now. Could be even millennium. Who knows what those Greek philosophers were thinking about but didn't write down. And we want to, I guess, overall try and shape chaos into something that we can use and maybe describe a bit better. And so there are different fields dedicated to studying chaotic systems to try and make sense of them. For example, if you think about the atmosphere, it has many, many, many more particles than we can ever keep track of. It's just such a complex system. And even if we connected, say, all the computers together today and tried to run a simulation of what happens in the atmosphere in 1 second, it would take thousands or even millions of years to try and simulate just 1 second of all the particles moving in the atmosphere. So this is truly a system that we can't really trace and define, but we still have models. We have atmospheric models that are able to take this extremely large system that's impossible to model on the point scale And we're still able to predict the weather for the next morning, or even we're getting pretty good with a couple days out, unless you live in a coastal area, in which case it tends to be wrong. So meteorologists are able to take this extremely complex system and simplify it in a way that it's a bit easier to understand, and we can actually make predictions about it. Now, the idea of taking these large complex systems and simplifying them with, say, just a few generic properties is what thermodynamics is about. Now, thermodynamics itself analyzes how groups of individual particles behave as a whole. So it takes some averaging here and essentially treats this system as something with definable properties, even if the particles themselves are chaotic. And this has produced pretty reliable results. Now, while we have yet to have, I think, a very in-depth discussion of thermodynamics, and we may have to dedicate an episode to that, and also statistical mechanics, there are regions of thermodynamics that I want to discuss today that pull from chemistry, physics, and engineering. And this is how we as a human species have used thermodynamics to our advantage, and how it came about in a really monumental time in the world, reigning in these complex systems under just a few equations. And this started to make our world smaller and, to say, turn faster and faster with progress. Now, this aspect of thermodynamics that helped the world so much is, of course, engines. Now, thermodynamics actually came about for the desire to increase the efficiency of steam engines. So engines didn't fall from some sort of theory saying, oh, well, if we did this type of thing, then we get an engine. No, people were playing with steam engines for many decades before they were actually described mathematically. In the late 1700s, early 1800s, right around the period of the start of the Industrial Revolution. And it was French physicist Sadi Carnot who first proposed the idea of improving the steam engine. Now, Carnot's ideas were for helping the Napoleonic Wars and hopefully winning them for France. Didn't happen. But Lord Kelvin actually was, I guess, the first person involved with actually describing a concise definition of thermodynamics. And part of that was based on the work of Carnot, who was working in the early 1800s. Now, Carnot introduced what was later called the Carnot cycle. Of course, Carnot didn't name it after himself. That's for other people to do. And this cycle determines the transfer of heat between two thermal reservoirs, which are just reservoirs with two different temperatures. So an example of a reservoir is, for example, your house and the outside. If it's cold outside, it might be warmer in your house, especially if you're in Canada right now. So you have two thermal reservoirs. And the difference between the temperatures of these two reservoirs makes all the difference. Because when you have energy being transferred from the colder reservoir to the hotter reservoir, it can do work on the system. And so this is where the principles of different engines come in, where you, especially steam engines that run under an actual Carnot cycle, not the ideal Carnot cycle that Carnot came up with in the first place. And now the hotter and colder that these reservoirs, or the bigger the temperature difference between them, the more efficient the engine will be, up to maximum efficiency, which is the ideal Carnot cycle. Now, the total work that can be done on the system does depend on the temperature of the two systems. So more work can be done. So if you're able to get, say, in a steam engine, a much hotter steam, and then have it much colder outside, you'll have a much more efficient engine. Now, while Carnot was able to describe his ideal system, the real world applications were a more efficient steam engine, which was becoming more exponentially present at the time of Carnot. Now, the steam engine itself and making it more efficient became pivotal in the development of industrialization within the world. And there were many different engine types that were developed based on the ideas of Carnot and also A couple other famous people that you may have heard of, including Watt, Trevithick, Stirling, and Otto, who all came up with different versions of different types of engines. Now, there were some gas engines and diesel engines in there, but steam engines, especially coal-powered steam engines, were very prevalent at the time. And even if they weren't directly involved with the development of steam engines specifically, their work and their theories that went on to contribute to the overall body of thermodynamics helped improve all engines. So there were a lot of different advancements in steam engines during the time. So the earliest steam engine that we know of was actually not quite as we see it today, but was described by Hero of Alexandria, who was a Greek mathematician and an engineer in Roman Egypt, who essentially said, oh, well, if we boil water within a vessel that has two oppositely pointing nozzles, then it will spin. So this was a very rudimentary steam engine. And it took until around 1700 that pumping engines were actually used to pump water, especially out of mines that were very deep down. So they could use these pumping stations to draw water out and make it easier to mine. Now, coal is mined. Coal was used to run these engines, and eventually we got piston steam engines, which were used the pressure of steam to push a piston. And so these would have at least two pistons working in them, where one would be pushed up while the other is pushed down, and the steam is cleared out, and it would just cycle through that. Now, it wasn't until later, around 1800, that we actually had high-pressure steam engines. And Watt is actually well known. So Watt, the person who you might closely associate with light bulbs or power use or joules per second, but he got his start with steam engines, and particularly developing the high-pressure steam engine. Now, this high-pressure steam engine was pretty revolutionary, and instead relied on a vacuum of condensing steam to pull a piston instead of pushing one, and these engines were actually a lot more efficient. So eventually they said, oh, well, what if we turn a steam engine onto its side, put it on wheels, maybe put it on a track, and have it go forwards? This ended up producing a much more powerful steam engine and much more compact by putting it on its side. And thus was the introduction of railways and trains and even some early cars by just placing a steam engine on its side. So the steam engine was pretty pivotal in advancing the world. So it went from improving the workplace of mines to cars and eventually connecting continents together. And it really is what industrialized the world, based on just a couple very simple equations that describe how the steam engine works. Now, there's also a lot of advanced engineering that went into it, but concepts from the steam engine age are still present today, like the steam turbine, which still generates most of the electricity that we use, because even everything from nuclear power and coal to natural gas plants all use steam turbines to generate power. Now, during this special time of development in the early 1800s to late 1800s, we saw the advancements of humans as well as the advancements of thermodynamics, and they almost matched each other in terms of advancements and ideas. And while the world became smaller because of steam engines and everything that they could do, the world of thermodynamics became a lot larger as physicists were able to describe these complex, chaotic systems in almost a neat, orderly way. Now, there is still a lot to figure out about chaotic systems, and also a lot of work still going into thermodynamics, like in statistical mechanics, but the efforts of people almost 200 years ago still apply today to these intensely complex systems. And I'm excited to see where this research and these developments go as they continue to pair with each other through the coming centuries.
All right. Thank you, Patrick, for the interesting story about how the world is connected in one way.
Thank you for that. And again, thanks to Josh for joining us.
Yeah,
it was
fun.
a good time. We learned some stuff. And I guess we'll see everybody next time. Thanks for listening.
Take care.
Bye, everyone.